Welcome back to the deep dive. Today, we are taking a massive leap forward in your understanding of materials science.
We really are.
If our previous dives focused on the theoretical blueprints of crystals, all those beautiful lattices, symmetries, and unit cells, this deep dive is about the experimental powerhouse that lets us actually measure those atomic blueprints.
That's right. For you, the learner, this is the essential bridge. We are focusing entirely on X-ray diffraction, specifically Chapter 11, Geometry, which explains how the measurement works.
So this is the how-to guide.
Exactly. The mission today is to give you a fast but thorough understanding of the principles that govern how radiation interacts with ordered matter, culminating in the foundational laboratory techniques.
Okay, so we're going to cover where X-rays come from, derive the fundamental law of diffraction, visualize this geometry using a brilliant conceptual tool called the Ewald sphere,
Which is a lifesaver for getting your head around this stuff.
and then walk through the mechanics of the experiments you see in every materials lab, the powder and Laue methods.
You know, this transition from abstract theory to actionable science was one of the most significant breakthroughs in 20th century physics. It completely changed our ability to map the world at the atomic scale.
To really set the scene, you have a quote for us, right?
I do. It's from William L. Bragg in 1922, and it really captures the elegance of the discovery. He said, "In trying to think of some way in which diffraction effects with X-rays might be found, he von Laue came to the realization that nature had provided, in a crystal, a diffraction grating exactly suited for that purpose."
A built-in diffraction gradient. I just love that idea that the regularity of the crystal lattice is precisely what we exploit. Okay, let's start with the tool itself, the X-ray.
Let's do it.
So section 11.2 starts with a definition. X-rays are electromagnetic waves traveling at the speed of light, a staggering, 299,792,405 meters per second.
Unbelievably fast. But what makes them special, the characteristic that allows them to interact with atomic lattices, is their extremely short wavelength.
And that's the key, isn't it?
It is the absolute key. Unlike visible light, which has wavelengths in the hundreds of nanometers, X-rays typically range from, let's say, 0.101 to 1 nanometers.
Okay, and why is that range so critical?
Well, because useful diffraction only occurs when the wavelength of your probing radiation is comparable to the distance between the things scattering it. In a crystal, that's the atomic centers. You basically need a ruler the same size as the thing you're measuring.
That makes perfect sense. And we attribute the discovery, of course, to Wilhelm Conrad Röntgen. Now, when we discuss X-rays, physics always brings up this concept of dual nature.
Yes, wave-particle duality. We have to consider them both as waves and as particles.
So sometimes it's a photon, sometimes it's a wave.
Exactly. Sometimes the energy properties, the photon aspect, are more relevant, and sometimes, like for diffraction geometry, the wave aspect is paramount. For our purposes today, the wave is key.
So what is that wave?
It's an oscillating electric field and a magnetic field, perpendicular to each other. Now, if we were to try and write this down mathematically, in classical terms, we'd use a simple sinusoidal expression, something like EXTT equals 2.
Okay, and that just links things like wavelength and frequency to the speed of light.
Right, psi is a lambda nu. But dealing with the complex three-dimensional geometry of a crystal lattice makes that standard wave equation, well, it gets unwieldy fast.
I can imagine. So the source mentions we transition to a highly specialized notation using complex exponentials. Now, we don't need to get lost in the calculus here, but what does this specialized math achieve for us conceptually?
It's all about separating the components of the wave. It's a very clever trick. Using Euler's formula, we arrive at an expression like E math BA T, math BA I T to P to faro later T. The main takeaway for you is that this notation allows us to cleanly split the wave's spatial behavior, which is the math BFT dot math BFT more, from its temporal behavior, the megatio part.
And since the atoms in the crystal are fixed in space, we only care about the spatial part.
Precisely. We can effectively ignore the time component for this geometric problem.
That brings us to the wave vector, math BFKev. This is where we really fully enter the realm of reciprocal space, right?
Yes, this is the first big step. The wave vector math BFKF is the critical link between the incident X-ray beam and the crystal structure. It's a vector that, as you say, resides in reciprocal space.
And it tells us two things.
Two very important things. First, its direction tells you the precise path the X-ray is traveling. Second, its magnitude, its length, is defined as the inverse of the wavelength. So 2K equals 1 lambda.
So a shorter wavelength means a longer wave vector. That seems simple, but I have a feeling this vector relationship is going to be incredibly important later on.
It's the foundation of the Ewald sphere. That vector math BFK is always oriented perpendicularly to the planes of constant phase, pointed right along the X-ray's direction. It basically packages all the input information about the radiation into one manageable reciprocal space vector.
So we know what X-rays are. How do we produce them reliably in a lab environment? We use an X-ray generator or an X-ray tube. What's the fundamental physics driving this?
It's a classic result from classical electrodynamics.
Yeah.
You get electromagnetic radiation whenever a charged particle, in this case an electron, accelerates, or more relevantly here, decelerates.
It's breaking radiation, essentially.
That's one part of it, yes. And the X-ray tube is basically a very controlled particle accelerator. It starts at the cathode, typically a heated filament.
And the heat causes electrons to just boil off.
It does. It's a process called thermal emission. Then we apply a huge potential difference, a high voltage dollar-dollar, between that cathode and a heavy metal target, which we call the anode.
And that high voltage zaps the electrons across the gap.
It does more than that. The electrons are subjected to an enormous electric field, and their potential energy, EP equals EVA, is converted directly into kinetic energy, EK equals 12 meter V22.
That's where the high velocity comes in. I saw a number in the source that for a potential of just 10,000 volts, these electrons are moving at approximately 59.3 million meters per second.
That's right.
That's almost 1/5 the speed of light.
That incredible velocity is necessary because the electrons need a huge amount of kinetic energy to smash into the dense anode target and cause a rapid, violent deceleration.
And here's where the stark reality of the process hits home. The source notes that only about 1% of that kinetic energy actually produces the desired X-rays. 1%. What happens to the other 99%?
It's converted almost entirely into thermal energy, just heat. Lattice vibrations, electron excitations, it just dissipates.
Which has some pretty major practical implications.
Oh, absolutely. It's why laboratory X-ray generators are often large, heavy, and require these elaborate cooling systems, usually with circulating water. This 99% inefficiency fundamentally limits how much power we can safely pump into a standard X-ray tube before the target literally melts.
Wow. Okay, so focusing on that productive 1%, the maximum energy of the X-ray photons is directly governed by the incoming electron's kinetic energy. This leads to a fundamental boundary called the short wavelength limit, lambda.
Correct. The photon energy 11 is related to wavelength by 1 egali equals h/c lambda. Since the maximum energy the photon can possibly have is AJ levels from the accelerating voltage, we can rearrange this.
And that defines the absolute minimum wavelength you can get.
It does. Lambda min is 1239.8 begalier, where the wavelength is in picometers. So if you increase the accelerating voltage, you shorten lambda min, making your X-rays more energetic, more penetrating. But crucially, no X-ray produced by that tube can be shorter than this limit.
So if we plot the spectrum, the intensity versus the wavelengths, we see two major features. The first is a broad background curve.
That background is the continuous spectrum, known as Bremsstrahlung.
The breaking radiation we mentioned.
Exactly. You can think of it as static or noise. It results from the random deceleration of electrons as they're scattered by the target nuclei. It's continuous because the electrons lose energy in all sorts of different amounts, producing a whole range of photon energies up to that sharp lambda min cutoff.
So that's the general noise. But sitting on top of that noise are the sharp, intense spikes we actually use for diffraction. Those are the characteristic peaks.
And these are the precise signals we want. Unlike the Bremsstrahlung noise, they originate from quantum mechanics. The high-energy incident electrons strike the target atoms and they physically knock out inner shell electrons. Most critically, those in the K shell.
Which leaves the atom unstable.
Very unstable. And nature abhors a vacuum, so an electron from a higher shell, say the L shell or M shell, drops down to fill that vacancy.
And in doing so, it has to release energy.
Precisely. It releases a specific quantized amount of energy in the form of an X-ray photon. And because those electronic energy levels are fixed and unique to the target material, be it copper, molybdenum, or iron, the resulting wavelengths are a characteristic fingerprint of that element.
Which we call the Tex alpha line for the L to K transition and Tex beta for M to K.
And we typically use the Tex alpha line because it's the most intense. It's the strongest signal.
It's amazing how a simple choice, like using a copper target versus a molybdenum target, completely changes the energy and wavelength of your tool.
It changes the entire experiment.
So for most precise diffraction analysis, we absolutely need a monochromatic beam, a beam dominated by a single wavelength. But looking at the spectrum, we always have that strong but unwanted Tex beta peak right next to our desired Tex alpha peak. We need a way to filter the beam.
We do. And the method relies on the principle of attenuation by absorption. Any material you place in the path of the X-rays will reduce the beam intensity, $O.
And this follows Beer's law for X-rays.
That's right. I$ is a linear absorption coefficient. We often standardize this by dividing by density, giving us the mass absorption coefficient Terry-Ho, which depends only on the material and the wavelength.
So this is where the physics of the absorbing material becomes our filter.
Yes. If you plot that mass absorption coefficient against wavelength, you see a general trend. Shorter wavelengths, which are higher energy, are absorbed less. But then all of a sudden, there is a dramatic, sharp spike, a discontinuity. We call it the K-absorption edge.
So why does the material suddenly become opaque to X-rays right at that specific energy? What's happening?
It's because that specific energy corresponds exactly to the energy required to eject an electron from the K-shell of the absorbing atom.
Wow.
So once the X-ray photon has just enough energy to break that tightest bond, the probability of absorption skyrockets. The atom becomes incredibly efficient at capturing that energy, leading to a massive spike in absorption at that precise wavelength.
And that's the key. We can exploit this. We can use that absorption edge to selectively remove the text-beta radiation while letting the text-beta radiation pass through. So how do we choose the filter material?
The rule is simple and elegant. We use a thin metallic foil whose atomic number, 0 is exactly 1 less than the target element, so Z001.
So for a copper target, which is Z298,
Use a nickel filter, which is Z028.
and the placement of nickel's K absorption edge is the strategic factor here.
It is. The nickel K absorption edge falls precisely between the text alpha and text beta lines of the copper source. The higher energy text beta photon has just enough energy to get absorbed very strongly by the nickel.
Because it's just above nickel's K edge.
Right. But the lower energy text alpha photon is just below the K edge, so it passes through with minimal attenuation.
And the numbers are impressive. The source says filtering can improve the text beta intensity ratio from about $7, $5.11 to $500.11.
It's a dramatic improvement. That reduction in unwanted background signal is what allows crystallographers to get clean, interpretable diffraction patterns. Without it, the peaks would overlap, and structure determination would be pretty much impossible.
Okay, so with our purified monochromatic X-ray beam, we're ready to introduce the crystal lattice. The source uses a great analogy to introduce diffraction, visible light passing through finely woven fabric.
It's a perfect analogy. If you take a laser pointer and shine it through a piece of cloth, you don't just see a big blurry spot. You see a set of discrete, ordered spots on the wall.
Right.
The fabric is a two-dimensional, ordered array of tiny holes, and that pattern of light spots directly reflects the regular arrangement of the threads.
And what's the profound takeaway from that simple analogy?
It's the crucial insight of the reciprocal relationship. The diffraction pattern is the image of the reciprocal lattice, not the real space lattice.
Okay, what does that mean exactly?
Yeah. It means that if the spacing between the threads in the fabric is very small, the resulting diffraction spots, the image will be spaced far apart if the threads are spaced widely in the fabric.
The spots will be very close together. Small in real space means large in reciprocal space, and vice versa.
Exactly. We can't directly see the atoms, but we can measure this reciprocal image, and then we mathematically deduce the real structure from that image. The crystal structure exists in real space, but all our experimental data lives in reciprocal space.
So the phenomenon that governs whether we see a bright spot or no spot at all is wave interference, which depends entirely on the phase difference,
Right.
3Lx.
Atoms scatter X-rays continuously. But for us to detect a signal, the X-rays scattered from billions of atoms in the crystal must be in phase. They have to reinforce one another.
And that reinforcement depends on the path difference.
It does. If two waves scattered from adjacent atoms travel slightly different distances, that path difference, delta, dictates the phase shift. We calculate the phase difference relative to the wavelength.
And constructive interference, a bright spot, only happens when that path difference is an integer multiple of the wavelength.
Right, when delta x ln da. Any other path difference leads to partial or total cancellation. The crystal acts as a selective filter, only scattering intensity in very specific directions where this phase condition is perfectly met.
This precise condition for constructive interference leads us directly to the core geometric requirement for diffraction, established by W. L. Bragg and his father in 1912, Bragg's law.
And to get there, they simplified the model. Instead of thinking about individual points, they treated the crystal as an infinite stack of parallel, equally spaced planes of atoms.
So you define the spacing between those planes as dolars, and the incident angle that is the angle between the incoming X-ray and the plane itself.
Yes, the Bragg angle. And then you just ask, what's the condition for constructive interference?
We are the path length difference between a wave reflecting off the top plane and a wave reflecting off the plane right below it to be an exact integer number of wavelengths.
And a little bit of geometry shows that this path difference is exactly 2 sin theta.
Which gives us the most fundamental equation in structural analysis, 2 in theta and lambda.
It's just remarkably elegant. It links the material property we want to measure to the experimental variables we control, the wavelength lambda and the angle theta. For a fixed material and a fixed wavelength, diffraction will only occur at discrete, predictable angles.
And the integer number is the order of diffraction. The source mentions that we often absorb $1 into the definition of the Miller indices. Can you clarify that?
Certainly. So imagine you have a first-order reflection, so $1 one, from the $100 planes. That happens at a specific angle. Now, if you look for the second-order reflection where $1 if it's 2, the equation is 2 sin theta, it's 2 theta.
Okay.
You can mathematically treat that second-order reflection as if it were a first-order reflection coming from a hypothetical set of planes with half the spacing. $d$2.
I see.
So in modern practice, we just index that second-order reflection as $200, where the indices themselves account for that division of the spacing. For our discussion, we usually just assume on a level 1 and let the Miller indices Begunna-Skeller define the actual spacing Dellers.
The power of this is its predictability. If a researcher knows they have a cubic material like copper, they know the formula for Deller, they know their wavelength. They can then predict the exact angle where the 100-lever planes should diffract.
Exactly. The source shows the prediction for copper. $2 diddler should be 43.374 seker for $111 and $50.50 for $200. This ability to link a structural constant, the lattice parameter idal, to a precisely measured angle is what makes X-ray diffraction a quantitative science.
If your measured angle doesn't match the prediction, something is wrong.
Something is wrong with your crystal, your structure, or your measurement.
Okay, Bragg's law is clean, but when you look at it, it's hard to imagine how you solve for an entire three-dimensional crystal structure using just that one equation. This is where we need a better way to visualize the solution, isn't it?
Absolutely. Bragg's law only tells you if a reflection exists at a specific angle for a single plane. To map the entire 3D reciprocal lattice, we need a geometric tool. And that tool is the Ewald sphere, a conceptually beautiful construction from Paul Ewald.
Okay, let's establish the geometry. We know that reciprocal lattice vectors, math BSGL, are always perpendicular to the real space planes, payless, and their length is the inverse spacing. $1 lambda.
Right. So now imagine we fix the reciprocal lattice of our crystalline space. We take our incident X-ray wave vector, math BFK, which has a length of $1 lambda. We draw a sphere with that radius, $1 lambda.
Okay, a sphere with a radius equal to the length of our wave vector.
Yes, but here's the trick. The sphere is centered not at the reciprocal lattice origin $, but at the starting point C of the vector math BFK. The endpoint of math BFK is placed exactly on the reciprocal lattice origin $.
So the sphere is positioned relative to the incoming beam, and the crystal's reciprocal lattice points are fixed.
And the geometric genius is this. The Bragg condition for diffraction is satisfied if and only if a reciprocal lattice point, math BSG Dewey, falls precisely onto the surface of this Ewald sphere.
So if a reciprocal lattice point touches the surface, boom, you get a reflection.
You get a reflection. The vector connecting the center of the sphere, C, to that point, G, is the diffracted wave vector, math BFG.
So this instantly solves the problem of orientation.
It does. The vector relationship math BFG must hold. And because this is elastic scattering, the incident and diffracted waves have to have the same energy, so their magnitudes must be equal, math BFG 1 lambda.
And the Ewald sphere guarantees that because both math BFK and math BFK are radii of the same sphere.
Exactly. So instead of grinding through complex trigonometry, a crystallographer can just visualize the reciprocal lattice rotating. And every time a point sweeps across the sphere, they know a reflection will occur. It converts a complex algebraic problem into a simple geometric intersection problem.
It's a brilliant shortcut.
Yeah.
But the Ewald sphere also reveals a fundamental physical constraint on what we can measure, something called the limiting sphere.
It does. It comes right out of Bragg's law. We know that sin theta has to be between 1 in dollars and plus dollars.
Right.
Well, if we look at the equation sin theta lambda TD dollar, the largest value sin theta can take is $1. This means we must have lambda liti dollar. You simply can't get a reflection from a plane whose spacing to dollars is too small relative to your wavelength lambda.
So what does that mean in reciprocal space?
Since the magnitude of the reciprocal vector dollars is $7, the constraint becomes little lambda.
And that defines the limiting sphere.
Yes, it's a larger sphere centered at the origin of the reciprocal lattice with a radius of 2 lambda. Any reciprocal lattice point that falls outside this sphere is physically inaccessible.
It doesn't matter how you rotate the crystal.
It doesn't matter. The Ewald sphere, with its smaller radius of $1 lambda, can never reach those points. This sets a hard limit on your resolution. If you have a crystal with very small lattice parameters, a standard X-ray source might simply not be able to see those planes.
So the choice of wavelength is absolutely critical. Okay, we've established the theory. Diffraction happens when a reciprocal lattice point intersects the Ewald sphere. Now, how do we force that intersection to happen in the lab?
There are two primary strategies. Strategy 1, keep the incident beam and the Ewald sphere stationary and mechanically rotate the crystal and its reciprocal lattice until a point sweeps across the sphere surface.
And strategy 2.
Keep the crystal stationary and adjust the X-ray beam itself, which effectively means rotating or changing the size of the Ewald sphere until it intersects a stationary lattice point.
And the main experimental methods are all based on one of these two strategies.
Correct. The powder diffractometer is the workhorse. Monochromatic radiation, variable angle. The Laue method is the opposite. Polychromatic radiation, stationary crystal. And then you have more specialized techniques like Weissenberg and precession. We're going to focus on the two main characterization methods, powder and Laue.
Great. Let's start with the powder diffractometer. You see these everywhere in material science labs. Its fundamental characteristic is the sample itself. It's a powder.
A polycrystalline material, yes. A fine powder containing thousands, millions of tiny, randomly oriented crystallites or grains.
And that randomness is the secret ingredient.
It is. The Bragg condition requires a very specific orientation. If you had a single crystal, you would have to meticulously rotate it in 3 dimensions to find every single peak. With a powder, the random orientation guarantees that for every possible set of lattice planes, some fraction of the crystallites will always be oriented correctly to diffract at any given moment.
It's a statistical certainty. This leads us to the standard geometric setup, the Bragg-Brentano geometry. How does the rotation of the sample and the detector work?
This setup is designed for optimal focusing. The sample sits horizontally at the center. We use a monochromatic X-ray beam. The geometry dictates that the sample surface rotates at an angle theta, and the detector is mechanically linked to rotate at exactly twice that angle, $2 theta.
So it's a peta-theta scan. Why that specific ratio?
Think of it like a perfect bounce off a mirror. If the reflecting plane in the crystal rotates by, say, $10 degrees relative to the beam, the reflection angle changes by $20 degrees. The detector must follow that $2 theta path to capture the signal. This linkage ensures that all the diffracted beams converge exactly at the detector slit, maximizing intensity.
And as this measurement proceeds, the detector sweeps across a range of $2 theta values, plotting intensity versus angle.
Exactly. And every time a specific set of planes in one of the oriented grains satisfies Bragg's law, we record a sharp peak.
The resulting pattern is a unique fingerprint of the material. What are the key applications for this kind of data?
First and foremost is qualitative phase identification. You measure the $2 theta position of every peak, use Bragg's law to calculate the corresponding Doppler spacing, and then compare that unique sequence of dollar spacings to vast standardized databases, like the powder diffraction file or PDF database.
So you can quickly verify if you made the compound you intended to make.
Or if your sample contains unwanted impurities. Beyond that, it's used for quantitative analysis, like determining precise lattice parameters. Small changes in composition or temperature cause small shifts in the peak positions, which we can measure with incredible accuracy.
Okay, before we had computer-controlled detectors, film was the medium of choice. The Debye-Scherrer camera is the historical example of this.
It was ingenious for its time. A cylindrical camera, maybe a few centimeters in radius, lined with photographic film. The powder sample is mounted as a tiny cylinder right at the center, and a monochromatic X-ray beam passes through it.
So what does the random orientation of the powder sample produce in this setup?
When Bragg's law is satisfied for a particular plane, say the $111 plane, all the randomly oriented crystallites reflecting at that moment do so symmetrically around the axis of the incident beam. This creates a cone of diffracted radiation.
A full cone?
A full cone for every set of planes. And those cones intersect the cylindrical film to produce symmetric arcs or rings.
So the analysis becomes a simple matter of measuring a physical distance on the film itself.
Precisely. The diffraction angle $2 theta is measured by the distance ladder between corresponding arcs on the film. Since you know the camera radius true dollars, the relationship is purely geometric. $2 theta, it was a robust way to get quantitative data from a piece of film.
Now we shift completely to the Laue methods, which represent the total opposite strategy from powder diffraction. We use a stationary single crystal.
And critically, we use polychromatic X-rays, the continuous Bremsstrahlung spectrum.
So what's the logic there?
It's simple but brilliant. If the crystal is stationary, the angle theta and the spacing's fixed. If you only had one wavelength, the probability of satisfying 2 deletion theta lambda would be basically 0.
Right, you'd have to be incredibly lucky.
But by supplying a continuous spectrum of wavelengths, you guarantee that for every fixed dollar and fixed beta, there is always some available wavelength lambda that will satisfy the equation.
So how do we visualize this in terms of the Ewald sphere?
The Ewald sphere suddenly gains depth. Since we have a range of wavelengths, we have a range of radii, $1 lambda. The sphere is no longer a single surface, but a volume contained between two concentric spheres.
So it's a shell, not a sphere anymore.
Exactly. The outer boundary is defined by the shortest wavelength, lambda min, and the inner by the longest, lambda max. Any reciprocal lattice point that happens to fall within that shell will find its corresponding wavelength and diffract, producing a spot.
And the resulting pattern is this complex constellation of spots, which depends entirely on the orientation and symmetry of the single crystal.
It's a direct map of the symmetry.
Okay, we have two main setups here. Let's start with transmission Laue.
In transmission Laue, the beam passes through the crystal, and the detector is placed directly behind it. The analysis of the resulting spot pattern reveals that spots belonging to planes that share a common crystal axis zone will be arranged on the film along the curves of ellipses.
And the second method is reflection Laue.
In reflection Laue, the detector is placed in front of the crystal. The beams reflect back toward the source side. This is for thicker or more absorbing samples. In this case, spots belonging to a common zone are arranged along hyperbolic curves.
The pattern is a direct visual map of the crystal symmetry. But how on earth does a crystallographer decipher this complex pattern of dots to figure out the crystal's orientation?
It requires sophisticated tools like the Greninger chart. The core challenge is converting the 2D spot locations on the film into a 3D description of the crystal's orientation. The Greninger chart lets you map the spot positions onto stereographic coordinates,
Which is just a standardized way to map the 3D angular relationships onto a flat 2D projection.
Correct. Since the arrangement of ellipses or hyperbolas reveals the twofold, threefold, or fourfold axes, mapping these spots onto a stereographic projection allows researchers to quickly identify the major crystallographic directions, like 100 or a 111, relative to the incoming beam.
So the Laue technique is an essential, rapid tool for just determining the orientation of a single crystal. It's the geometric key to unlock the symmetry.
That's a great way to put it.
We've covered extensive ground in this deep dive into the geometry of X-ray diffraction.
We certainly have. We started by understanding the generation of X-rays via accelerated electrons, producing both the Bremsstrahlung noise and those precise characteristic peaks we need.
Then we learned how the K absorption edge is strategically used in filtering to select a pure monochromatic beam.
And from there, we established the geometry of wave interference, which leads directly to Bragg's law, 2 sen theta and lambda.
That law links the internal atomic spacing of the material to the measurable external angle of the diffracted beam.
And we showed how the Ewald sphere provides the necessary geometric visualization, translating the complex angular requirements of Bragg's law into a simple intersection condition in reciprocal space.
Right, and that visualization also reveals a fundamental physical limit on our resolution, the limiting sphere, with a radius of $2 lambda.
Finally, we applied all these principles to the practical methods. The X-ray powder diffractometer, which uses monochromatic X-rays and random crystallite orientation to efficiently measure dollar spacings for phase identification.
And the Laue method, which uses stationary single crystals and polychromatic radiation to map crystal orientation and symmetry. X-ray diffraction truly uses the crystal's inherent order as the perfect measuring instrument.
That brings us to our final provocative thought for you, the learner. We know the limiting sphere dictates resolution based on that radius, 2 lambda. Now imagine a researcher is trying to determine the structure of a novel material that has extremely compact, small lattice parameters.
So that would mean very large reciprocal lattice vectors, Z dollar.
Very large. And they find that their standard copper source is physically incapable of resolving the structure because the points they need to see are outside the limiting sphere.
So what is the practical, real-world upgrade they have to save up for? And why does it solve this problem of the limiting sphere?
To expand that limiting sphere and access those fine structural details, they need to shorten the wavelength, lambda. This requires X-ray sources capable of delivering much higher energy photons, and that often necessitates a trip to a major research facility, a synchrotron, where electrons are accelerated to near light speed, generating ultra-high energy short wavelength X-rays capable of reaching the furthest corners of the reciprocal lattice.
The geometry always holds, and sometimes the solution to a technical problem simply requires a bigger machine. Thank you for joining us for this deep dive into X-ray diffraction geometry.
Until next time.